in this lecture we'll answer two questions. In the first question, we find out the perimeter of this quadrilateral ABCD, and in the second question, we'll find out the area of this green shape. So let's start with the first question. In the drawing we have quadrilateral ABCD. We know that AP equals to PD. This is line 7BQ. This equals to 10 units in its length. This is line 7PQ. This equals to 20 units in its length. This is line 7QC. This equals to 40 units in its length. Those three angles are all right angles. Again, our task is to find out the perimeter of this quadrilateral ABCD. What is a perimeter? A perimeter of a quadrilateral is the sum of its four side lengths. That is to say, it is equals to AB plus PD plus DC plus CB. That is the perimeter of this quadrilateral ABCD. So in the first step, we'll do a construction, that is to say, we'll do perpendicular on side AD at point P. But again, we'll do a perpendicular on side AB at point P. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. In the next step, we'll extend the perpendicular from point P until it touches the side BC of this quadrilateral ABCD. And we'll define the touching point of the extended perpendicular from point P and side BC. This point is point M. Here we can implement rule 18. Repeat quickly on rule 18. According to rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they lie between parallel lines. In the drawing, we have those two angles, alpha and beta, are defined as one-sided interangles. So if alpha plus beta equals to 180 degrees, then they are located, those two one-sided interangles are located between parallel lines. That is to say, line A is parallel to line B. So you can actually implement rule 18 in our drawing. In our drawing, those two angles, they are both defined as one-sided interangles. The sum of those two one-sided interangles is of course equals to 180 degrees, and therefore according to rule 18, those two one-sided interangles are located between parallel lines. That is to say, AB is parallel to PM. So if you found out that side AB is parallel to line 7 PM according to rule 18. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore according to rule 18, those two one-sided interangles must be located between parallel lines. That is to say, PM is parallel to DC. So according to rule 18, PM is parallel to side DC of quadrilateral ABCD. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, AB is parallel to DC. According to rule 18. AB is parallel to DC. So according to rule 18, those three line segments AB, PM and DC, they are all parallel to each other. So in the drawing, we have three parallel lines. AB is parallel to PM, and PM is parallel to DC, and also AB is parallel to DC. And whenever you have three parallel lines that are connected together by other two line segments, those three parallel lines are connected together by line segment AD and also by line segment BC. And according to the basic proportionality theorem, a special relationship exists between those two line segments AD and BC that connects the three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC. Again, AP over PD equals to BM over MC. So I write it down. According to the basic proportionality theorem, the following relationship exists between those two line segments AD and BC that connects the three parallel lines together. AP over PD equals to BM over MC. And again, according to the basic proportionality theorem, AP over PD equals to BM over MC. It is given us the question that AP equals to PD. So if we define the length of line segment AP as X, then line segment PD must be also equal to X because they are equal to each other according to what is given us the question. So AP over PD is X over X, and it is equals to BM over MC. X over X is 1, so 1 equals to BM over MC. Here we will multiply the equation by MC, and finally we get that MC equals to BM. So if you found out that this is line segment BM, that is equals to line segment MC. That is to say, point M is the midpoint of BC. Why? Because at point M, BC is been bisected into two halves. The first half is BM, and it is of course equals to the second half MC. And each half must be equal to BC over 2 because BC is bisected into two halves. So if you found out that BM, the first half BM equals to the second half MC, and each half must be equal to BC over 2 because BC is been bisected into two halves. BC in total equals to BQ, that is 10, plus QC, that is 40. So in total BC equals to 10 plus 40, that is 50. So in the non, BC equals to 10 plus 40, that is 50. So it is 10 plus 40 over 2, so BC over 2 is 50 over 2. 50 over 2 is 25. And from this long equation, we will derive that BM equals to MC equals to 25. So if you found out that this is line segment BM that equals to 25 units in its length, Likewise, this is line segment MC, that is also equals to 25 units in its length. What is the length of this missing line segment? Line segment QM. From the drawing, it is very easy to see that QM in total equals to BM minus PQ. So write it down. QM in total equals to BM minus BQ. So QM equals to BM is 25, minus BQ is 10. So in total QM equals to 25 minus 10, that is 15. QM equals to 15 units in its length. This is the missing line segment QM, that equals to 15 units in its length. In the next step, we will implement the Pythagoras theorem on this right green triangle, triangle PQM. But again, we will implement the Pythagoras theorem on this green right triangle, triangle PQM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. This right green triangle PQM, according to the Pythagoras theorem, PM squared, that is the square of the hypotenuse, equals to PQ squared plus QM squared. And again, in this right green triangle PQM, according to the Pythagoras theorem, PM squared, that is the square of the hypotenuse, equals to PQ squared plus QM squared. PM is the missing side, so we leave it as it is, so it is PM squared equals to PQ squared. PQ is 20, and therefore PQ squared is 20 squared, that is 400. Plus QM squared. QM is 15, and therefore QM squared is 15 squared, that is 425. So in total, we shall find out that PM squared equals to 400 plus 225, that's actually 625. So PM squared equals to 625. Here we will take a root out of this equation and find out that the missing hypotenuse PM is equal to the square root of 625, that is actually 25 units in its length. This is the hypotenuse of this green triangle PQM, and it is equal to 25 units in its length. In the next step, we'll do another construction, that is to say, from point M, we'll do perpendicular on DC. Again, from point M, we'll do perpendicular on DC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point M and side DC. This point is point N. By doing this construction, we can do quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth facing angle, in total the must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth facing angle must be equal to 90 degrees in its size. So in quadrilateral PM and D we have 4 right angles, and therefore quadrilateral PM and D is a rectangle. In the next step, we define this angle, that is angle QPM, as alpha. So this right triangle QPM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. BC is one side of quadrilateral ABCD, and therefore it is absolutely a straight line. So if we focus on the right side of the straight line BC at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line BC at point M? We have this angle that is equal to 90 degrees minus alpha. This is the right angle plus this third missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, so 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha. So the sum of those two angles is equal to 180 degrees minus alpha. And therefore, this third missing angle must be equal to alpha. 1 equals 90 degrees minus alpha plus alpha is 180 degrees. Again, 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of the angles on the right side of the straight line BC at point M according to rule 3. And therefore this first missing angle must be equal to alpha. So in the lower right triangle M and C, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. So in a rectangle PM and D, the opposite sides are equal to each other. That is to say, side PM is equal to the opposite side DN. But PM is 25, and therefore the opposite side DN must be also equal to 25 units in its length. In the next step, we will prove that those two right angles can go into each other according to angle side angle rule. That is to say, this is the green right triangle PQM. It is congruent to this right lower triangle M and C according to angle side angle rule. So what those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two sides That is to say PM and MC. They are both the hypotenuses of those two right triangles. They are both equal to 25 units in their lengths, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees bounce alpha, and therefore they are equal to each other. So if you prove that those two right angles can go into each other according to angle side angle rule. That is to say, you should prove that those two angles and the side that is included between those two angles, that is side PM of this right triangle PQM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC on this right lower triangle MNC. And therefore those two right angles can go into each other according to angle side angle rule. So I write it now. This is the right triangle PQM. It can went. This is the sign of congruent to this right lower triangle MNC according to angle side angle rule. Repeat again. We actually found out that the upper green right triangle PQM can point to the lower right triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that those two sides must be also equal to each other. Those two corresponding sides must be also equal to each other in their lengths. According to the rule that states that corresponding sides and congruent triangles are equal to each other, those two triangles can go into each other, and therefore those two corresponding sides, that is to say PQ and M and MN, must be also equal to each other in their lengths. But PQ equals to 20, and therefore the corresponding side MN must be also equal to 20 units in itself according to the rule that I mentioned. So MN equals to 20. Likewise, according to the same rule, those two corresponding sides must be also equal to each other in their lengths. But QM is 15, and therefore the corresponding side NC must be also equal to 15 units in itself, according to the same rule that says that corresponding sides and congruent triangles are equal to each other. So NC, the corresponding side NC, must be equal to 15 units in its length. So, in rectangle PM and D, side MN must be equal to the opposite side PD. But MN is 20, therefore the opposite side PD must be also equal to 20 units in its length. PD equals to X and X equals to 20. So X equals to 20. But AP is also X, and therefore X equals to 20, that is to say AP also equals to 20 units in its length. Repeat again. According to what is given in the question, AP equals to PD. So if PD equals to 20, then AP must be also equal to 20 because they are equal to each other in their lengths. So the only missing side that is left to find out is this side AB. In order to find out the length of side AB, we will implement the Pythagoras mid-segment theorem on this quadrilateral ABCD. First of all, quadrilateral ABCD is a trapezoid. Because any quadrilateral that is a trapezoid is a quadrilateral with one pair of parallel sides. In quadrilateral ABCD, side AB is parallel to the opposite side DC, according to Rule 18. Again, AB is parallel to DC. And therefore, quadrilateral ABCD is a trapezoid. those two parallel sides, that is to say AB and DC, are defined as the bases of this trapezoid ABCD, while the other two sides that are not parallel to each other, that is to say AB and BC, are defined as the legs of this trapezoid ABCD. So what is the definition of line segment PM? Line segment PM bisect the leg AD. Why line segment PM bisect the leg AD? Because point P is the midpoint of AD. That is to say, at point P, side AD has been bisected into two halves. The first half is AP, that is equals to 20, and it is of course equals to the second half of AD, that is PD, that is also equals to 20 units in its length. So point P is the midpoint of the leg AD. Likewise, here point M bisect side BC. Why point M is bisect side BC? Because point M is the midpoint of BC. That is to say, at point M, BC has been bisected into two halves. The first half is BM, that is equals to 25, and it is of course equals to the second half MC, that is also equals to 25 units in its length. And each half, of course, equals to BC over 2, that is 50 over 2, that is 25. BC in total is 50, and each half equals to 50 over 2, that is 25. BM equals to 25, and the second half MC also equals to 25 units in its length. So actually, trapezoid mid-segment theorem talks about the length of this mid-segment PM. PM is the mid-segment because it bisects the leg AD and also bisects the leg BC. So already mentioned before. So the trapezoid mid-segment theorem talks about the length of this mid-segment PM. According to trapezoid mid-segment theorem, the length of mid-segment PM equals to the sum of its two parallel bases over 2. That is to say, it is AB plus DC over 2. So until now, we shall find out that according to trapezoid mid-segment theorem, the length of mid-segment PM of trapezoid ABCD is equal to the sum of its two parallel bases, that is to say, it is AB plus DC over 2. Repeat again. According to trapezoid mid-segment theorem, the length of the mid-segment PM, the length of mid-segment PM is equal to the sum of its two parallel bases, that is to say, it is AB plus DC over 2. But we already found out that PM equals to 25, therefore we can substitute PM by 25. And it is equals to AB. AB is the missing side, so we leave it as it is. Plus DC. DC in total equals to DN, that is 25, plus NC, that is 15. So DC in total equals to 25 plus 15, that is 40. Divided by 2. In total, if we found out that 25 equals to AB plus 40 over 2. Here we multiply this equation by 2, and finally we get that 25 times 2 is 50, so 50 equals to AB plus 40. Here we will subtract 40 from this equation, and finally we get that the missing side AB, in total it is equal to 50 minus 40 is 10. So AB equals to 10 units in its length. But again, this is the missing side AB, this is equals to 10 units in its length. the perimeter of this trapezoid ABCD, that we can define also as quadrilateral ABCD, it is equal to the sum of its four side lengths. That is to say, it is AB, that is 10, plus AD, that is 40, 10 plus 40 is 50, plus DC, that is 40, 50 plus 40 is 90, plus BC, that is 50, so 90 plus 50 is 140 units. So the perimeter of trapezoid ABCD is equal to 140 units in its length. So I write it down. The perimeter of quadrilateral ABCD, that it is actually trapezoid ABCD. In total, it is equal to the sum of its four side lengths. That is to say, it is equal to AB plus AD plus DC plus BC. And again, the perimeter of this quadrilateral ABCD equals to the sum of its four side lengths. This is to say, it is equal to AB plus AD plus DC plus BC. So it is equal to AB. AB is 10 plus AD. AD is 40 plus DC. DC is also 40 plus BC. BC equals to 10 plus 40, that is 50. So in total, we found out that the perimeter of quadrilateral ABCD equals to 10 plus 40 is 50, 50 plus 40 is 90, 90 plus 50 is 140 units in its length. The perimeter of quadrilateral ABCD, it is equal to 140 units in its length. That is the answer to the question. Then again, the perimeter of this quadrilateral ABCD is equal to 140 units in its length. In the next step, I will present to you another way to find out that the length of this side AB is equal to 10 units. According to the first method, we use the trapezoid mid-segment theorem in order to find out that AB equals to 10. In the second method, we will do another thing. That is to say, from this point B, we will draw perpendicular on PM. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point B and side PM. This point is point S. By doing this construction, we can do the right triangle BSM. In the right triangle BSM, this angle equals to 90 degrees minus alpha. This angle equals to 90 degrees according to our construction, and therefore this third angle must be equal to alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we will prove that this is the upper right triangle BSM. This can go into this lower right triangle MNC according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those are the hypotenuses of those two right triangles. They are both equal to 25 units in their lengths, and therefore they are equal to each other. BM equals to 25, and the hypotenuse MC also equals to 25, and therefore they are equal to each other in their lengths. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we should prove that those two right angles can go into each other according to angle side angle rule. That is to say, we should prove that those two angles and the side that is included between those two areas, that is actually side BM, in this right triangle BSM, are corresponding equal to those two areas, and the side that is included between those two areas, that is actually side MC, in this right triangle MNC. Therefore, those two right triangles can go into each other according to angle side angle rule. So I'll write it down. I found out that this is the upper right triangle BSM. And it's congruent to this lower right triangle MNC. According to angle side angle rule. And again, if you found out that the upper right triangle BSM congruent, this is the sum of congruent to the lower right triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that those two corresponding sides must be also equal to each other their lengths. That is to say, side SM of this right triangle BSM is equal to the corresponding side NC on this right triangle MNC. So those two sides are equal to each other according to the rule dimension. But NC is 15, and therefore the corresponding side SM must be also equal to 15 units in its length. SM equals to 15 units in its length. What is the length of this missing 97 PS? From the drawing, it is very easy to see that PS in total equals to PM minus SM. So already known. If we found out that PS in total is equal to PM minus SM. So PS in total equals to PM. PM is 25 minus SM. SM is 15. So in total PS equals to 25 minus 15, that is 10. PS equals to 10 units in its length. This is, let me say 97 PS, it equals to 10 units in its length. So, in the small quadrilateral, first of all, this is quadrilateral APSB. In this small quadrilateral APSB, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in size, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral ABSP we have 4 rectangles, and therefore quadrilateral ABSP is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this upper rectangle ABSP, side AB must be equal to the opposite side PS. But PS is 10, and therefore the opposite side AB must be also equal to 10 units in its length. Unfortunately, if you found according to the second method, that AB equals to 10 units in its length. So we found out that AB equals to 10 units in its length in 2 different methods. And the final answer to this question is that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. So we finish with the first question. In the next step, I will present to you the second question, and we'll solve the second question of this lecture. this second question, our task is to find out the area of this green shape. So in the drawing we have two semicircles. This is the big semicircle with the diameter AB. Inside this big semicircle we have this small semicircle with the diameter PQ. It is given us the question that this is line segment AC, it is equals to 4 units in its length. This is line segment CB, that is equals to 6 units in its length. Again, our task is to find out the area of this green shape. So first of all, when we find the center of this big semicircle, this point is point O. And when we find the center of this small semicircle, this point is point S. Likewise, when we find the radius of this small semicircle, Sx. So the radius SQ equals to x. Likewise, the radius SP of this small semicircle also equals to x units in its length, according to our definition. We know that AB is the diameter of this big semicircle. AB in total equals to AC, that is 4, plus CB, that is 6. So in total AB equals to 4 plus 6, that is 10. So, adding on. The diameter AB of the big semicircle is equal to 4 plus 6, that is 10. The diameter over 2 is the radius of this big semicircle. So we define the radius of this big semicircle as capital R. So capital R equals to the diameter AB over 2. So it is 4 plus 6 over 2. So the diameter capital R equals to 10. The radius of the big semicircle equals to the diameter AB, that is 10 over 2. 10 over 2 is 5. So we found out that the radius of the big semicircle, capital R, equals to 5 units in its length. This is the radius OB, it equals to 5 units in its length. This is the radius OA, it also equals to 5 units in its length. In the next step, we will join points S and C together by straight line. Point S is the center of this small semicircle. Point C is the point of the small semicircle itself. Therefore, SC is the radius of this small semicircle, is equals to x. The radius SC is equals to x. The radius of SC of this small semicircle is drawn to point C, that is the point of tendency of tangent AB with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius QS. If AB is perpendicular to QS, if AB is perpendicular to CS, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size, according to Rule 1. In the next step, we will do another construction. That is to say, from point P, that is the touching point of this small semicircle with this big semicircle. So from point P, we will draw perpendicular on AB. Again, from point P, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size, according to our construction. We define the touching point of the perpendicular from point P inside AB. This point is point M. What is the definition of line segment MP? MP is a tangent to this small semicircle at point P. So MP is a tangent. This is the radius SP, that is equals to x. there speed is equals to x is drawn to point P, that is the point of tendency of tangent AMP with this small semicircle. Whenever your radius is drawn to the point of tendency, then tangent MP will be perpendicular to the radius PS. If MP is perpendicular to PS, it means that this angle equals to 90 degrees according to rule 1. So inside this small quadrilateral PMCS, we have 1, 2, 3 arteries, and therefore this fourth angle must be equal to 90 degrees in its size. So in the small quadrilateral PSCM, we have 4 arteries, and therefore quadrilateral PSCM is at least a rectangle in front of the square. So we relate to quadrilateral PSCM as a rectangle because it has 4 rectangles. So this is rectangle PSCM. We know that the opposite sides of a rectangle are equal to each other. So in rectangle PSCM, side PS must be equal to the opposite side MC. But PS is x, therefore the opposite side MC must be also equal to x units in its length. And this same rectangle PSCM, according to the same rule, that the opposite sides of a rectangle are equal to each other, we will side SC of rectangle PSCM is equal to side PM on this rectangle, but SC is x, and therefore the opposite side PM must be also equal to x units in its length. What is the length of this short line segment? Line segment AM. From the drawing, it is very easy to see that AM in total equals to AC minus MC. So, write it down. I should found out that the length of the short line segment AM in total it is equals to AC minus MC. So AM equals to AC. AC is 4 according to what is given as the question. So AM equals to 4 minus MC. We just find out that MC equals to x. So in total AM equals to 4 minus x units in its length. AM equals to 4 minus x units in its length. In the next step, we will do a construction. That is to say, we will complete this big semicircle to a circle. So we completed this semicircle to a circle. And then we'll extend tangent PM by straight line until it touches the circle. We define the touching point of the extended tangent PM with this circle. This point is point N. PM is a tangent to this semicircle at point P. So PM as a tangent, it is absolutely a straight line. We extended the straight line PM by a straight line, the result is a PN. It's PN. We extend the straight line by a straight line, the result PN must be also a straight line. So PN is a straight line. So if you focus on the right side of the straight line PM at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles here at the right side of the straight line PM, the right side of this straight line PN at point M, you have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Point O is the center of this big circle. From point O, we have perpendicular OM on chord PN. Again, from point O, that is the center of this big circle, we have perpendicular OM on chord PN. So here we can implement rule 15. So I'm just quickly on rule 15. According to rule 15, a perpendicular from the center of a circle to any chord bisects the chord. In the drawing we have a circle. This is point S, that is the center of this circle. From point S, we have perpendicular ST on chord MN. Again, from point S, it is the center of this circle, we have perpendicular ST on chord MN. And according to this rule, rule 15, perpendicular ST bisects chord MN. If ST bisects MN, it means that ST divides MN into two halves. The first half is MT, and it is, of course, equal to the second half TN. Each half must be equal to MN over 2. Why? Because MN has been bisected into two halves. So the first half MT equals to the second half TN, and each half must be equal to MN over 2 because MN has been bisected into two halves. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, from the center of this big circle, that is to say from point O, we have perpendicular OM on chord PN. And according to rule 15, perpendicular OM bisects chord PN. That is to say, perpendicular OM divides chord PN into two halves. The first half is PM, and it is of course must be equal to the second half MN, and each half must be equal to PN over 2. So I write it down according to rule 15. Perpendicular OM to chord PN bisects chord PN. The first half of PN is PM, and it is of course must be equal to the second half of PN, that is MN, and each half must be equal to PN over 2 because PN has been bisected into two halves. Repeat again, we should find out that perpendicular OM bisects chord PN. So the first half PM must be equal to the second half MN. And perpendicular OM bisects chord PN. The first half of PN is PM, and it is of course equal to the second half, that is MN. So PM equals to MN, according to rule 15. But we already found out that PM equals to X. So we can write here that PM equals to X. And from this equation, X equals to PM equals to MN. We derive that MN must be also equal to X units in its length. According to 15. So this is 9/7 mn. It is also equals to x units in its length, according to rule 15. In the next step, we will implement rule 24 in our drawing. So I'll repeat quickly on rule 24, and we will implement the rule in our drawing. According to rule 24, rule 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. And again, in the drawing we have a circle, this is chord AB that intersects with chord CD at point O. The intersection point between AB and CD is at point O. So whenever you have two chords that intersect with each other, then the following equation is true. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. Why? Because in our drawing, we have chord AB, that is actually the diameter of this big circle. Chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. So all the requirements for rule 24 are satisfied, and therefore we can implement here rule 24. So I write it down. We should find out that chord AB intersects with chord PN at point M. Okay, again, now what you're doing, chord AB intersects with chord PN at point M. So all the requirements for rule 24 are satisfied, and therefore we can implement rule 24 in our drawing. According to rule 24, the following equation is true, that AM times MB equals to PM times MN. And again, according to rule 24, the following equation is true. That AM times MB equals to PM times MN. We already found out that AM equals to 4 minus X units in its length times MB. What is the value of MB? MB total equals to MQ, that is X, plus QB, that is 6. So in total, MB equals to X plus 6 units in its length. And it is equals to PM times MN. PM is X, MN is also X, so PM times MN is X times X, that is X squared. So in total, we should find out that 4 minus X times X plus 6 equals to X squared. Here we will open the brackets of this side, on this side of the equation, and we get that 4 times X is 4X, and we have 4 times 6 is 24, minus X times X is minus X squared, and we have minus X times 6 is minus 6X equals to X squared. So in total we found out that 4X plus 24 minus X squared minus 6X equals to X squared. So here we have 4, on this side of the equation we have 4X minus 6X is minus 2X. We have also 24 plus 24 minus X squared equals to X squared. So here we'll add x squared, we'll add x squared to this equation. And so here x squared plus x squared is 0, so x squared is cancelled. Here we have x squared plus x squared is 2x squared equals to minus 2x plus 24. So here we add 2x to this equation. If I can get that two x squared plus 2x equals to 24. And again, if you found out that two x squared plus 2x equals to 24. Here we will subtract 24 from this equation. And we can get that 2x squared plus 2x minus 24 equals to 0. Here we will divide this equation by 2, and finally get that 2x squared over 2 is x squared, 2x over 2 is x, so this is plus x, minus 24 over 2 is minus 12, equals to 0 over 2 is 0. So we found out that x squared plus x minus 12 equals to 0. So here, this is a quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x. What is x? X is the radius of this small semicircle. The coefficient a in our specific quadratic equation equals to 1. The coefficient b also equals to 1. And the coefficient c equals to minus 12. So we have all the data that is needed in order to find out the variable that we are looking for, that is x, that is the radius of the small semicircle. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way we'll find out the value of the values of x, because x, this quadratic equation might have two solutions. So we'll do it now, and we'll get that x equals to minus b. b is minus 1, so minus b is 1, so minus b is minus 1. Plus minus square root of b squared. b is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. So it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. c is minus 12, so minus 4 times 12 is plus 48. So inside the root we have in total 1 plus 48 over 2a. a is 1, so 2a is 2 times 1, that is 2. So in total we actually found out that x equals to minus 1 plus minus 1 plus 48 is 49. So inside the root we left only with 49 over 2. So in total we should find out that x equals to minus 1 plus minus the square root of 49 is 7 over 2. This again. We actually found out that x equals to minus 1 plus minus 7 over 2. So here we will have two solutions for x. The first solution for x is that x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So if you found out that according to the first solution for x, x equals to minus 4. But x, the variable that we are looking for is x, that is the radius of this small semicircle. X is the length, is the length of the radius of this small semicircle. So x is a length, it must be a positive number, therefore it can never be equal to minus 4, that is a negative number. So cancel the first solution for x, and we take into account only the second solution for x. The second solution for x is x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. According to the second solution for x, x equals to 3 units in its length. So the radius of this small semicircle x equals to 3 units in its length. Our test is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total equals to the area of the big semicircle. The radius of the big semicircle equals to 5. The radius of the area equals to 5. Minus the area of this small semicircle. So it is minus the area of the small semicircle. We already found out that the radius of this small semicircle equals to 3 units in its length. So in total we found out that the area of the green shape, that is the area that we are looking for in this question, is equals to the area of the big semicircle minus the area of the small semicircle. So the area of the big semicircle must be equal to pi r square over 2. R is 5, so it is pi 5 square over 2. Minus the area of the small semicircle. The radius of the small semicircle is 3, and therefore the area of the small semicircle must be equal to pi times 3 square over 2. So here we take 2 as a common factor from those two expressions. So here in this side, in the numerator of this expression, we have in total 25 pi. Also in the numerator of this expression, we have 9 pi. So it is minus 9 pi over 2. 25 pi minus 9 pi is 16 pi over 2. 16 pi over 2 is 8 pi. And there are some numbers, it is equal to 25.13 square units in size. Okay, again, I should found out that the area that we are looking for this question, this is the area of this green shape. In total, it is equal to either 8 pi square units in size, or in terms of numbers, it is equal to 25.13 square units in size. So we finished to answer on the second question. In the next step, I'll summarize the lecture. That is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question. the first question, our task was to find out the perimeter of this quadrilateral ABCD. What is a perimeter? A perimeter is the sum of those four side legs of this quadrilateral ABCD. That is to say, it is equal to AB plus AD plus DC plus CB. So in the drawing we have quadrilateral ABCD. We know that this is AP equals to PD. This is line segment BQ, that is equals to 10 units in itself. This is line segment QP, that is equals to 20 units in itself. This is line segment QC, that is equals to 40 units in itself. Those three angles are all right angles. Again, our task is to find out the perimeter of this quadrilateral ABCD. It is actually equals to the sum of its four side lengths. It is actually AB plus AD plus DC plus CB. So in the first step, we did the construction, that is to say, we do perpendicular on AD, it's point P. Again, we do perpendicular on side AD, it's point P. So this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. In the next step, we extended the perpendicular P by side line until it touches side BC. We define the touching point of the extended perpendicular P with side BC. This point is point M. Okay, so by doing this construction, we have here and those two right angles that are defined as one-sided interangles. And according to Rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. The sum of those two one-sided interangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM. Repeat again, if you found out that AB, side AB is parallel to side PM according to Rule 18. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore they must be located between parallel lines. Those two one-sided interangles must be located between parallel lines. That is to say, PM is parallel to DC. Again, PM is parallel to DC according to the same rule, Rule 18. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, AB is parallel to DC. You can see that AB is parallel to DC according to the same rule, Rule 18. So in the drawing, we have three parallel lines. AB is parallel to PM, and is parallel to DC. Those three parallel lines are connected together by AD and also by BC. And then you have three or more parallel lines that are connected together by other two line segments. You can implement a basic proportionality theorem on the drawing. According to the basic proportionality theorem, the following relationship exists between AD and BC that connects the three parallel lines together. The relationship is as follows: AP over PD equals to BM over MC. And again, according to the basic proportionality theorem, the following relationship exists between AD and BC that connects the three parallel lines together. The relationship is as follows: AP over PD equals to BM over MC. But AP equals to PD, according to what is given in the question. So if AP is X, then PD must be also equal to X because they are equal to each other. So AP over PD is X over X equals to BM over MC. X over X is 1, so 1 equals to BM over MC. You multiply this equation by MC, and find out that MC equals to BM. So if you found out that BM equals to MC, And therefore point M is the midpoint of BC. It's point M, BC is bisected into two halves. The first half is BM, and it is of course equal to the second half MC, and each half must be equal to BC over 2 because BC is bisected into two halves at point M. So the first half of BC is BM, and it is of course equal to the second half of BC, that is MC. Each half must be equal to BC over 2 because BC is bisected into two halves. So each half must be equal to BC over 2. But BC in total equals to BQ, that is 10, plus QC, that is 40. So BC in total equals to 10 plus 40. Here BC equals to 10 plus 40 over 2. 10 plus 40 is 50, and 50 over 2 is 25. So from this long equation, we know that BM equals to MC equals to 25. That is to say BM, this is 97 BM, that is equals to 25 units in length, and this is 97 MC, that is also equals to 25 units in length. So BM equals to 25, BQ equals to 10. Therefore, this BC 97 QM must be equal to BM plus BQ. Again, QM equals to BM plus BQ. So QM in total equals to BM, that is 25, plus BQ, that is 10. So in total, QM equals to 25 constant, that is 15. This is the missing sign QM, this is equals to 15 units in its length. In the next step, we implemented the Pythagoras theorem on this right range triangle PQM. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle PQM, it means that PM squared, that is the square of the hypotenuse, equals to PQ squared plus QM squared. So again, in the right triangle PQM, according to the Pythagoras theorem, PM squared equals to PQ squared plus QM squared. PM is the missing side, so we leave it as it is, so it is PM squared equals to PQ squared. PQ is 20, therefore PQ squared is 20 squared, that is 400, plus QM squared. QM is 15, therefore QM squared is 15 squared, that is 225. So in total, we found out that PM squared equals to 400 plus 225, that is 625. So PM squared equals to 625. Here we took out of this equation, and we found out that the missing hypotenuse PM is equals to the square root of 625, that is 25 units. So the hypotenuse PM equals to 25 units in its length. In the next step, we did another construction, that is to say, from point M, we do perpendicular on DC. Again, from point M, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and DC. This point is point N. By doing this construction, we get the div quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 angle. In total, it must be equal to 360 degrees. According to the rule, it's said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 angle must be equal to 90 degrees in the size. So in quadrilateral PM and D, we have 4 right angles, and therefore quadrilateral PM and D is a rectangle. In the next step, we define the size of this angle QPM as alpha. So in the green triangle PQM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. BC is one side of quadrilateral ABCD. So BC is a side of a quadrilateral, it is absolutely a straight line. So if we focus on the left side, from the straight line BC at point M, Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the side line is equal to 180 degrees. So which angles we have at the left side of the side line BM, on the left side of the side line BC at point M, we have this angle that is equal to 90 degrees minus alpha, plus this is a right angle, plus this third missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha. So the sum of those two angles, total is 180 degrees minus alpha, plus this third missing angle, in total must be equal to 180 degrees. And therefore, this third missing angle must be equal to alpha. 1 equals 180 degrees minus alpha, plus alpha equals to 180 degrees. That is the sum of the angles on the left side of the side line BC at point M according to rule 3. Therefore, this missing angle must be equal to alpha. So in this lower right angle M and C, this angle equals to alpha. This angle equals to 90 degrees. And therefore, this first angle must be equal to 90 degrees minus alpha according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right angles can go into each other according to angle sine angle rule. That is to say, we actually prove that this is the green right triangle PQM, that it is congruent to this right lower triangle MNC according to angle sine angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, the hypotenuse PM equals to the hypotenuse MC. They are both equal to 25 and therefore they are equal to each other. So we found out that MC equals to 25. So both hypotenuses are both equal to 25 and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you prove that those two right angles can go into each other according to angle sine angle rule. That is to say, we prove that those two angles and the side that is included between those two angles, that is side PM in this right triangle PQM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC in this right lower triangle MNC. Therefore, those two right angles can go into each other according to angle side angle rule. Okay, again, I'm sure we prove that the green right triangle PQM can go. This is the sign of congruent to the right lower triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that those two sides must be also equal to each other in their lengths, according to the rule that said that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. That is to say, side PQ of this green triangle must be equal to side MN of this right lower triangle MNC. But PQ is 20, therefore the corresponding side MN must be also equal to 20 units in its length. Likewise, according to the sum rule, those two sides must be also equal to each other in their lengths. Okay? According to the sum rule that said the corresponding sides in congruent triangles are to each other, those two corresponding sides must be also equal to each other in their lengths. But QM equals to 15 units in its length, and therefore the corresponding side NC must be also equal to 15 units in its length. So in total, this equals to 25 plus 15, this is 40. This is rectangle PM and D. In rectangle PM and D, the opposite sides are equal to each other. That is to say, side PM equals to the opposite side DN, but PM is 25, and therefore the opposite side DN must be also equal to 25 units in its length. Likewise, according to the sum rule, in the sum rectangle PM and D, side MN must be equal to the opposite side PD. But MN is 20, therefore the opposite side PD must be also equal to 20 units in its length. PD equals to X, and X equals to 20. So X equals also to 20. This is to say EP is equals to X is also equals to 20 units in its length. So we found out all the three sides length of this quadrilateral ABCD. The only missing side that is left to find is this side AB. First of all, quadrilateral ABCD is a trapezoid. Why? Because quadrilateral ABCD is one pair of parallel sides. That is to say, side AB is parallel to the opposite side DC. We only found out that AB is parallel to DC according to rule 18, and therefore quadrilateral ABCD is a trapezoid. Those two parallel sides are defined as the bases of this trapezoid ABCD, while the other two sides that are not parallel to each other, that is to say AD and BC, are defined as the legs of this trapezoid ABCD. So here we can implement the trapezoid mid-segment theorem on our drawing. But again, this is trapezoid ABCD. What is the definition of this line segment PM? This is line segment PM. Line segment PM bisect the leg AD, because AP equals to PD. Likewise, line segment PM bisect the leg BC. At point M, the leg BC has been bisected into two halves. The first half BM equals to 25, and the second half MC also equals to 25 units in itself. So in total, we should found out that PM is the mid-segment of trapezoid ABCD because of the fact that PM bisects the two legs AD and BC. But what is the length of mid-segment PM? According to the trapezoid mid-segment theorem, the length of PM, it is equal to the sum of the two parallel bases of trapezoid ABCD, that is actually AB plus DC over 2. But again, the length of the mid-segment PM is equal to AB plus DC over 2. And again, according to the trapezoid mid-segment theorem, the length of mid-segment BM is equal to the sum of the two parallel sides of trapezoid ABCD. That is actually AB plus DC over 2. AB is the missing side, so we leave it as it is, plus DC. DC in total equals to 25 plus 15, that is 40. So we substitute DC by 40 divided by 2. So in total we found out that, again, according to what we already found out, PM, the mid-segment PM equals to 25. So in total we found out that 25 equals to AB plus 40 over 2. Here we multiply this equation by 2 and finally found out that 25 times 2 is 50, so 50 equals to AB plus 40. Here we subtracted 40 from this equation and finally found out that AB equals to 50 minus 40, it is 10. AB equals to 10 units in its length. This is the missing side AB, that equals to 10 units in its length. Our test is to find out the perimeter of this trapezoid ABCD or quadrilateral ABCD. The perimeter of this quadrilateral ABCD it is equal to the sum of its four side lengths. That is to say, it is AB plus AD plus DC plus CB. And again, the perimeter of quadrilateral ABCD or trapezoid ABCD is equal to the sum of its four side lengths, that is to say AB plus AD plus DC plus BC. AB is 10, AD is 40, DC is 40, BC is 50. 10 plus 40 is 50, 50 plus 40 is 90, 90 plus 50 is 140. So in total, if you found out that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. In the next step, I presented to you a second method to find out that AB is 10. According to the first method, we relied on the trapezoid mid-segment theorem in order to find out that AB equals to 10. In the second method, we will do a construction. That is to say, from point B, we did a construction. From point B, we do perpendicular on PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the turning point of the perpendicular from point B and PM. This point is point S. By doing this construction, we get here the upper quadrilateral ABSP. The upper quadrilateral ABSP, we have 1, 2, 3 angles. And therefore this fourth semicircle must be equal to 90 degrees in its size. So quadrilateral ABSP is 4 rectangles, and therefore quadrilateral ABSP is a rectangle. So in this right triangle BSM, this angle equals to 90 degrees minus alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to alpha according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle must be equal to alpha. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we prove that the upper right triangle BSM can go into this right lower triangle, triangle MNC, according to angle side angle rule. That is to say, right, those two right triangles can go into each other. First of all, those two angles are both equal to alpha, and therefore they are equal to each other. Likewise, the hypotenuse BM on this right triangle BSM equals to the hypotenuse MC on this right triangle MNC. They are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we actually prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we actually prove that those two angles and the side that is included between those two angles, that is side BM, on this right triangle BSM, corresponding equal to those two angles, and the side that is included between those two angles, that is side MC, on this right lower triangle MNC. So we actually prove that those two right triangles can go into each other according to angle side angle rule. And again, we found out that the upper right triangle BSM can go in, this is the same, can go into the right lower triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that those two sides must be also equal to each other and their lengths. According to the rule that corresponding sides in congruent triangles are equal to each other, those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other and their lengths. But NC is 15, and therefore the corresponding side SM must be also equal to 15 units in its length. What is the length of this piece in 97 PS? PS in total equals to PM minus SM. And again, PS in total equals to PM minus SM. So PS in total equals to PM, that is 25, minus SM, that is 15. So in total, PS equals to 25 minus 15, that is 10. So PS equals to 10 units in its length. So in rectangle ABSP, side PS must be equal to the opposite side AB, but PS is 10, and therefore the opposite side AB must be also equal to 10 units in its length. AB equals to 10. So we proved in two different methods that AB equals to 10 units in its length, and the perimeter of this quadrilateral ABCD is equal to 140 units in its length. So we finished to repeat on the first question. In the next step, I repeat on the solution of the second question. The second question, our task is to find out the area of this given shape. So in the drawing we have two semicircles. This is the big semicircle that contains this small semicircle. We know that this is line segment AC, this is equals to 4 units in its length. This is line segment CB, this is equals to 6 units in its length. Again, our task is to find out the area of this given shape. So first of all, we define the center of this big semicircle. This point is point O. Likewise, we define the center of this small semicircle. This point is point S. We define the radius of this small semicircle as x. So the radius is P equals to x. and the radius SQ also equals to x units in its length. AB is the diameter of this big semicircle. AB in total equals to AC, that is 4, plus CB, that is 6. So in total, AB equals to 4 plus 6, that is 10. So the diameter AB of this big semicircle equals to 10 units in its length. And again, the diameter AB equals to 4 plus 6, that is 10. Therefore, the radius must be equal to half of the diameter. That is to say, must be equal to AB over 2. That is 10 over 2 is 5. So the radius R of this big semicircle equals to 5 units in its length. In the next step, we join points S and C together by a straight line. Point S is the center of this small semicircle, point C is the point of the small semicircle itself, therefore SC is the radius of this small semicircle, that equals to x. The radius SC is equals to x, the radius SC is drawn to point C, that is the point of tendency of tangent AB with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did another construction, that is to say, from point P, that is the touching point between the big semicircle and the small semicircle. So from point P, we draw perpendicular on AB. Again, from point P, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AB. This point is point M. What is the definition of MP? MP is the tangent to this small circle, point P. So here we have the radius SP that is equals to x. The radius SP is drawn to point P, that is the point of tendency of tangent AP with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AP will be perpendicular to the radius PS. If AP is perpendicular to PS, it means that this angle equals to 90 degrees according to rule 1. So in total, inside this small quadrangle PSCM, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in its size, and therefore quadrangle PSCM is a rectangle because it has 4 rectangles. But we also know that the opposite sides of the rectangle are equal to each other. So in the small rectangle PSCM, side PS must be equal to the opposite side MC. But PS is x, therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the symbol, in the same small rectangle PSCM, side SC must be equal to the opposite side PM. But SC is x, therefore the opposite side PM must be also equal to x units in its length. So if you found out that quadrangle PSCM is not a rectangle but the square, one because of the fact that all of its sides are equal to each other, its side equals to x. So the small quadrangle PSMC is a square. What is the length of this short line segment AM? From the long, it's very easy to see that AM in total equals to AC minus MC. And again, AM equals to AC minus MC. So AM in total equals to AC, that is 4, minus MC, that is x. So in total, AM equals to 4 minus x units in its length. In the next step, we did the construction, that is to say, we completed this big semicircle to a circle. Then we extended tangent PM by its side line until it touches the circle. At this point, we define the touching point of the extended tangent PM with this circle. This point is point N. PM is a tangent to a circle. It is absolutely a straight line. When you extend the straight line PM by a straight line, the result PN must be also a straight line. So PN is a straight line. If you focus on the right side of the straight line PN, it's point N. Here the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PN at point M? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So in the drawing, point O is the center of this big circle. From point O, we have perpendicular OM on chord PN. Again, from point O, that is the center of this big circle, we have perpendicular OM on chord PN. And according to rule 15, a perpendicular from the center of the circle towards any chord bisect the chord. That is to say, perpendicular OM bisect chord PN. Repeat quickly on rule 15. According to rule 15, a perpendicular from the center of the circle to any chord bisects the chord. Then we have a circle. This is point S, that is the center of this circle. From point S, we have perpendicular ST on chord MN. And according to this rule 15, perpendicular MT, perpendicular ST bisects chord MN. That is to say, perpendicular ST divides chord MN into two halves. The first half is MT, and it is of course equal to the second half Tn, and each half must be equal to Mn over 2 because Mn has been bisected into two halves. So we found out that Mt equals to Tn, and it is equal to Mn over 2. So we can implement rule 15 in our drawing. In our drawing, as I already mentioned before, from the center of this big circle, we have perpendicular OM on chord Pn. And according to rule 15, perpendicular OM bisects chord Pn. So the first half is PM, and it is of course equal to the second half Mn, according to rule 15. And again, perpendicular OM bisects chord Pn. The first half of Pn is PM, and it is of course equal to the second half of Pn, that is Mn. So Pm equals to Mn according to rule 15. But we already found out that Pm equals to x, so we can write it that Pm equals to x, and from this equation x equals to Pm equals to Mn, we will have that Mn also equals to 6 units in its length. Mn equals to x units in its length. This is line segment Mn, that is also equals to x units in its length according to rule 15. In the next step, I presented to you rule 24, and we implemented rule 24 in our drawings. Repeat quickly on rule 24. According to rule 24 is shown in any circle. So in any circle with chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the drawing we have a circle, this is chord AB that intersects with chord CD at point O. So in this drawing the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 24 in our drawing. In our drawing, this is chord AB, that is the diameter of this big circle. Chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. So all the requirements of rule 24 are satisfied, and therefore we can implement rule 24. And again, if you found out that in our original drawing, chord AB intersects with chord PN at point M. So according to rule 24, the following equation is true, that AM times MB equals to PM times MN. Again, AM times MB equals to PM times Mn. So according to rule 24, the following equation is true, that AM times MB equals to PM times Mn. AM equals to AC minus Mn, that is actually 4 minus x. So substitute AM by 4 minus x times MB. MB total equals to MC, that is x, plus CB, that is 6. So in total, MB equals to x plus 6. So substitute MB by x plus 6. And it is equals to PM times Mn. PM is x, Mn is also x, and total PM times Mn is x times x, that is x squared. So in total, if you found out that 4 minus x times x plus 6 equals to x squared. Here we open the brackets on this side of the equation, and we found out that 4 times x is 4x, 4 times 6 is 24, and we have minus x times x is minus x squared, and we have also minus x times 6 is minus 6x equals to x squared. Here we have 4x minus 6x is minus 2x, plus 24 minus x squared equals to x squared. Here we add x squared to this equation, so x squared minus x squared is 0, so in this side of the equation we have to leave with 2x plus 24. In this side, in the other side of the equation we have x squared plus x squared, this is 2x squared. So in total we found out that minus 2x plus 24 equals to 2x squared. Here we add 2x to this equation, and finally found out that (2x squared plus 2x equals to 24). Here we subtract 24 from this equation, we finally found out that 2x squared plus 2x minus 24 equals to 0. Here we divided this equation by 2 and finally found out that 2x squared over 2 is x squared, plus 2x over 2 is x, minus 24 over 2 is minus 12 equals to 0 over 2 is 0. So in total we found out that x squared plus x minus 12 equals to 0. This is the quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0. To 0 equals the variable that we are looking for is x. X is the radius of the small semicircle. X is the radius of this small semicircle. The coefficient a in our specific quadratic equation, the coefficient a equals to 1, the coefficient b also equals to 1, and the coefficient c equals to minus 12. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value of the values of x, that is the values of the small semicircle. We did it, and we found out that x equals to minus b. B is 1, so minus b is minus 1, plus minus square root of b squared. B is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. So this minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. C is minus 12, so minus 4 times minus 12 is plus 48. So in total inside the root we have 1 plus 48 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total if you found out that x equals to minus 1 plus minus 48 plus 1 is 49, so inside the root we left only with 49 over 2. The square root of 49 is 7. So if you found out in total that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is 4. So the first solution for x is that x equals to minus 4. X is the radius of this small semicircle, that is to say x is the length, and x as a length, it must be a positive number. It can never be equal to minus 4, that is a negative number, so we cancel the first solution for x, and we took into account only the second solution for x. The second solution for x is as follows. X equals to minus 1 plus 7 over 2. So x equals to minus 1 plus 7 is 6, and 6 over 2 is 3. So if you found out that the radius of this small semicircle x equals to 3 units in its length. Our test is to find out the area of this green shape. The area of this green shape equals to the area of this big semicircle minus the area of this small semicircle. I repeat again, the area of the green shape, that is the area that you're looking for in this question, is equals to the area of the big semicircle with radius 5 minus the area of the small semicircle with radius 3. The area of the big semicircle equals to pi times the radius square over 2. The radius is 5, so it is pi times 5 square over 2. Minus the area of the small semicircle, it is equal to pi times the radius square over 2. So it is pi times 3 square over 2. Here we took 2 as a second factor out of these two expressions. So in the numerator we have 25 pi minus 9 pi divided by 2. 25 pi minus 9 pi is 16 pi over 2. 16 pi over 2 is 8 pi. 8 pi tells some numbers, it is 25.13 square meters in size. So if you found out that the area that you are looking for in this question, that is the area of this green shape, in total it is equal to either 8 pi square meters in size, or in terms of numbers, the area of this green shape is equal to 25.13 square meters in size. Okay, thank you very much.